In this video, we're going to talk about an application of Infra-Bayesianism called Infra-Bayesian Physicalism. By the end of the video, you will hopefully have an understanding of the problem that Infra-Bayesian Physicalism is trying to address and how it aims to accomplish this. So last video, we spoke about how Infra-Bayesianism can address the problem of non-realizability. However, there is another problem that standard reinforcement learning has, which relates to what is called the Cartesian boundary. Jack spoke about this when talking about Vanessa's research agenda, but briefly. In standard reinforcement learning, the world is neatly divided into two parts, the agent and the environment, and these only interact via a specific input-output channel, meaning the only way the agent affects the environment is through its outputs, so the selected actions, and the only way the environment affects the agent is through its inputs, so the observations and rewards. This leads to a bunch of problems, one of which was non-realizability, which Infra-Bayesianism addressed by allowing agents to express Knightian uncertainty about parts of the environment that they don't understand. Another issue is that in the real world, the agent is a part of the environment, and the environment can interact with the agent in ways outside of the input channel. For example, the agent could be altered or destroyed by the environment. But the concern we will be most worried about here is that standard reinforcement learning agents will think about the world from a privileged position. They receive observations and take actions from their specific vantage point, and their hypotheses, as a consequence, will be from this privileged position. This means the models of the world that standard reinforcement learning agents have must be specifically about observations and actions, not about fundamental properties of the world. For example, instead of being able to reason about Newton's laws, the agents reason about the pixels on a camera and how those will change. When a human might think about the world not from the personal perspective, reinforcement learning agents will struggle to do this. Here we will focus on this perspective problem and the issues that it causes. So why is this privileged perspective a problem? In reinforcement learning, the AI's hypotheses treat its perspective as unique. But the way we understand physics is that no individual has a privileged position. Instead, science aims to describe the world with theories that conform to Occam's razor, meaning they are simple and elegant. But these theories are not phrased specifically in terms of observations. They are phrased in terms of fundamental degrees of freedom of the world. When I say fundamental degrees of freedom of the world, I'm talking about the quantities that appear in physics equations. These quantities are simple in the sense that the equations that describe them are simple mathematically, but they are very difficult to relate to observations. For instance, Schrödinger's equation talked about quantum mechanical wave functions using a short mathematical equation. It isn't saying much about what you'll see with your eyes. We'll see in the next example, being bound to a privileged perspective makes it hard to leverage Occam's razor. So as an example, imagine an agent moving around the world, viewing observations through a camera on its head, and imagine a towel is thrown over the camera of our AI. Our AI might hypothesize that the universe has changed in some fundamental way. Maybe it has the hypothesis that once its pixels go black, they will remain black forever. This isn't too complicated to specify as a hypothesis for a Cartesian agent, since this only adds a bit of complexity. In the bird's eye view, this hypothesis is very complicated, since there is nothing special about the towel, and so having it affect physical laws is a very complex modification of physics. You can imagine trying to update quantum mechanics with a magical towel that causes the world to end. It would be very difficult. Now, recall that we talked about AIXRP agents. When we talked about that, we had a prior distribution that selected against complex hypotheses, and this was very useful. We should hope this towel hypothesis is complex, since it isn't a very likely one, and so hopefully Occam's razor won't give it much weight when considering how the world actually is. This example illustrates a key point about this perspective issue. From the bird's eye view, Occam's razor is a powerful tool for selecting among hypotheses, and has a lot of empirical evidence to back it up as a good procedure. However, in the subjective view, Occam's razor stops being a good criterion to base selection of hypotheses. Simple hypotheses from the privileged perspective can actually be quite bad, and so we lose a powerful tool that helps us reason effectively.
I'd say hypotheses that are, in some sense, objective versus hypotheses that are subjective about your personal experiences. They have different notions of what counts as simple versus complex. Like throwing a towel over the webcam is something that is pretty simple subjectively, but objectively maybe not quite so much, while something like I see, while a hypothesis that's like, I'm just going to see black forever, that's very simple to specify subjectively, but objectively it'd be like, what? Why would there be a law of physics that says the universe poofs out when somebody throws a towel on the webcam?
Yeah.
So I'd say that it's subjective versus more third-person hypotheses tend to have different things that they say are simple versus complex.
This naturally prompts the question, can an AI use physical laws in reasoning about its hypotheses? Since laws of physics say no observer has a privileged role, if we want to use physical laws to reason about a privileged hypothesis, we have to supplement a Cartesian description of the world with a set of rules for converting hypotheses to a bird's eye view. These are called bridge rules, and specifically they need to translate fundamental degrees of freedom in a physical theory to the observations of an agent, along with translating agent actions back the other way. The problem, though, is this leads to our hypotheses being considerably more complex, since each hypothesis has to state which set of bridge rules it's using. This can be a major obstacle for algorithms aiming to use hypotheses to make decisions. We also saw this leads to our agent not being able to leverage Occam's razor due to the complexity of the bridge rules. There are also other concerns that we will talk about in the next video.
One way I like to formulate this problem is I'm calling it the problem of privilege. So why the problem of privilege? Because all the classical, the way we classically think about, for example, reinforcement learning, what I call the classical cybernetic framework, where you have an agent that is taking actions and making observations, everything is formulated from the perspective of the agent, from the point of view of the agent. So the agent is kind of a privilege, regarded as a privilege point inside the universe. That's why I'm calling it the problem of privilege. And that's very different from how we reason when we're doing, for example, when we're doing science. When we're doing physics, we don't expect the laws of physics to have humans as somehow important variables inside the equation. The laws of physics, we expect them to be described by simple equations where the variables in those equations are some kind of fundamental degrees of freedom, some kind of quantum fields or whatever, strings, whatever, which are very remote from agents or humans or whatever. And this difference is really, really important because, for example, in the AXI model, we rank hypotheses by their description complexity. But this is the description complexity from the subjective point of view, not from the objective point of view. So on the one hand, the motivation for this Solomon of prior is Occam's razor. On the other hand, the way we use Occam's razor in AXI is very different from how we use Occam's razor in science because of this difference between the objective and subjective point of view. And this difference actually corresponds to some huge penalty in the description complexity because the translation between those 2 points of view, the translation from quantum fields, for example, to, pixels on the camera of your robot or like the photons in your eye or whatever, is very, very, very complex. And this, you can show that this leads to a whole host of problems.
So to summarize the last few slides, standard reinforcement learning agents think about the world from a privileged perspective. This makes it hard for them to reason about the world effectively, and it makes it hard for them to take advantage of Occam's razor. They could use physical theories, but in doing this, they have to specify bridge rules, which causes other problems, and so this isn't really an adequate way to solve the issue. So that's the problem of the Cartesian boundary and the privileged perspective. Now let's talk about Infra-Bayesian physicalism and how it's going to go about addressing this issue. We will see that in physicalism, we will use what Vanessa calls a bridge transform, but first let's talk about how physicalism is set up. IB physicalism is a way to have the hypotheses our agent thinks about be from a bird's eye view. We do this by having our hypotheses specify beliefs about two things, the physical universe, phi, and the computational universe, gamma. Specifically, elements of phi describe how the universe could be and evolve in time, and elements of gamma tell you about what the outputs of different computations will be. We'll go into more detail about these two things in the next few slides, so don't worry if it seems complicated for now. The hypotheses of an IB physicalism agent are going to be infra-measures over phi cross gamma. We'll also unpack this a bit more as well.
In Infra-Bayesian Physicalism, what we do is precisely switch from this kind of privileged subjective point of view to a bird's eye view. So instead of describing our hypothesis about the universe in terms of actions and observations, we're just describing them as there's some ontology, some notion of states of the physical universe. And there's also facts about computations, which we kind of operationalize as mappings from programs to outputs. So you can like talk about facts like 2 + 2 = 4. And an Infra-Bayesian physicalist hypothesis is a joint belief about the product space of this physical ontology and the space of mappings from programs to outputs. So in other words, a physicalist hypothesis is a hypothesis which is a joint belief about what the physical state of the universe is and what is true about computations.
Okay, so let's talk more about phi. Elements of phi capture the way the physical universe is and will develop, describing some fundamental degrees of freedom and how they change. There are a few ways this can be done. For this video, you can think of the elements as mappings. You have an element of phi, and this maps time to what the world looks like at that time. This isn't quite as general as what Infra-Bayesian physicalism can express. For example, general relativistic theories don't have a consistent notion of absolute time. But for this video, thinking of phi in this way will be suitable. Even in this simpler case, this sounds quite daunting, so let's look at some examples. So imagine a world with only a single particle moving in three-dimensional space. In this world, we can describe the universe at time t by giving the location of the particle at that time. One example of how the physical world could be is the particle is moving along the x-axis with speed 1. We can express this as the function f. It maps time t to a vector that captures the described motion. Another example is the particle is moving in a helix shape, and we can express this as the function g. The elements of phi will be different motions the particle could have in this case. You can imagine throwing in more particles to make this more complicated. We don't actually have to use particles necessarily, though. For example, we could use quantum fields. In this case, we talk about how the field develops in time instead of the location of a particle. This would be a different choice of phi. Or maybe we use macroscopic properties. If we have a table moving around in space, I could just say where the table is, instead of all the individual particles of the table. The nice thing is that each hypothesis can be phrased differently in terms of physical states. This means one hypothesis could think about the world in terms of particles, another in terms of quantum fields, and another in terms of macroscopic properties. Each hypothesis can use a different phi, and we have the freedom to figure out all of these at the same time.
So here's the cool part. It can actually vary with the hypothesis. You can have different state spaces for different hypotheses. You could have one state space that's like, all right, we're going to describe what type all of these atoms are and where they all are. You can have another one that's phrased in terms of quantum fields. You can have another one that's phrased in terms of macroscopic properties. It's unique to the hypothesis. There isn't one universal phi that must be a state space for everything. Every hypothesis can have its own phi.
You're probably thinking, this already sounds like it's going to be way too complicated for realistic problems, and so it won't be useful. Remember that Infra-Bayesianism lets us express Knightian uncertainty. So our hypotheses can comment on the bits we do understand to some extent, and we can be Knightian uncertain about everything else, which will be most of the physical universe. Okay, so now let's talk about gamma. Gamma describes what the outputs of different computations will be. The elements of this are also mappings, but instead of taking time in as an input, they take in a computation and map it to an output. As an example of an element of gamma, we could have a map that maps everything to 0, so it says every program will output 0. We can also have more complicated ones that make more realistic predictions, like the table that I've given here. It gets some things wrong, but also some things right. Hopefully this seems a bit more intuitive than phi. Each element of gamma makes predictions about what different computations will output. Okay, so that's the space we have hypotheses over, but what about the hypotheses themselves? Hypotheses are beliefs about the combination of the physical and computational world. The reason we want to consider both the physical and computational worlds together is because we want to be able to think about how each one relates to the other. For example, I might press a button in the physical universe that causes a computation to be run. The output of that computation will then show up on a screen somewhere in the physical universe, so these things can affect one another. As a specific example, a hypothesis could be, I'm Knightian uncertain about almost everything, except there is a program that if it returns 0, it means there is a specific particle on my left, and if it returns 1, that particle is on my right, though I don't actually know what the outcome of that program will be. Our hypothesis will be an infra-measure over phi cross gamma. For this video, you can think of this as a set of distributions. As I mentioned earlier, this lets us be Knightian uncertain. So the agent doesn't actually need to know anything about how these spaces actually work, but it can express the knowledge it does know in a way that lets it be uncertain about what it doesn't. We will also generally be using a simplicity prior, which in simple terms means we place lower weight on hypotheses that are generally more complex. This is similar to what we discussed in the AIXRP video. It lets us leverage the power of Occam's razor to help our agent weigh different hypotheses even without evidence. Okay, so we have our hypotheses, and these are in the bird's eye view, but we have a problem. The observations and actions are still in the subjective view, and we need to relate these to our hypotheses to update them, as well as to use our hypotheses to take actions. How do we resolve this?
Okay, but in the end, we have an agent that's supposed to take actions according to observations it sees. So how do we connect those two points of view, the objective bird's eye and the subjective point of view? And here is the interesting part, because we found that there's a mathematical object that we call the bridge transform, which allows us to connect those points of view, and it has all sorts of nice mathematical properties. So yeah, so basically all comes together.
What we do is use what Vanessa calls the bridge transform, as opposed to bridge rules. The difference is that the bridge transform is a mathematical object that doesn't affect the description complexity of hypotheses, and so it doesn't suffer the same issues as the bridge rules do. The key insight is to find the agent in the physical universe specified by the hypothesis. But how does the agent find itself in the physical universe? First note, we assume the agent knows its own source code. In computer science, this isn't too big of an ask. The agent then looks in the physical universe specified by the hypothesis, searching for where the program that corresponds to its source code is running. If it finds that source code running and receiving some inputs, it can check if those inputs are the same as the ones it sees as observations. This provides evidence for or against the hypothesis. If it can't find its source code in a hypothesis, then it can safely ignore that one, since it can be confident it exists. As an example, if I know I'm looking at a banana, and my hypothesis doesn't include me looking at a banana, then it isn't the universe I'm in, and so I can discard it. If it does include me in the banana, then great, it just got some evidence towards it. We're almost there, except what do I mean by look in the universe for your source code? How is that actually done? Well, the idea is we look at something called counterfactuals. Recall we have access to our source code, and we also have a belief about its output, since it's a computation and our hypothesis involves beliefs about gamma, the computational universe. Also recall that our hypothesis is a set of distributions. We can consider counterfactuals by looking at subsets of this set that assign different outputs to our source code. These are counterfactuals. If the physical world looks different in different counterfactuals, we say that the source code is running. Intuitively, this is because if the world doesn't change based on the outcome, then that outcome doesn't appear anywhere, and so the program wasn't being run. Or at least we are 90% uncertain about whether it's running. We have a spectrum in between these that gives different probabilities that the program is running. The nice thing here is that we can do this for any program we know about, so we can use this to check if some computation is being run in the universe. This will be necessary when we look at predicate. So as an example, suppose I have some program and I want to know if it's running. I look at the counterfactuals of it outputting 1 and outputting 0, meaning I look at the worlds in my hypotheses where the program outputs 1 or outputs 0. I then look at what the world typically looks like in these cases. Suppose I see the world is different in the two cases. For example, the oceans are different colors typically. It is likely the program was running and led to this change, since that's the only change I'm considering when I'm looking at these different sets of distributions.
The way it works is you can take some program and given a certain joint belief about physics and computation, because it's a joint belief, it allows for some entanglement between computations and a physical state. You could have a situation where when you consider counterfactuals, like in Infra-Bayesianism, you have a notion of counterfactuals. When you consider counterfactuals, so what happens if this program produces such output, whereas what happens if this program produces a different output? It can happen that the physical state of the universe is going to look different, or not. Maybe it's going to look the same. And then we're going to say that if it looks different, then it means that the universe is actually running this program. If it looks the same, then the universe is not running this program. So this is the kind of basic idea.
So now we've talked about how we can use observations to update our bird's eye view hypotheses. Let's talk about making decisions. In Infra-Bayesianism, we use the notion of a utility function to guide decision making. Here we will speak about loss functions. You can think of the loss function as a negative of a utility function. So maximizing your utility function is the same idea as minimizing a loss function. As was stated earlier, in standard reinforcement learning, loss functions are stated in terms of observations and actions. This makes it hard for agents to care about things they don't directly observe, which isn't ideal. For example, humans definitely care about things they don't directly observe. For instance, I would like people in Australia to be living meaningful lives, even if I don't directly observe it. In Infra-Bayesian Physicalism, loss functions are defined in terms of what computations are running, and roughly speaking, the outputs of those computations. This can encode lots of different things. For example, if some computation represents a human suffering, I can care about the universe in which this happens. As another example, I could have a loss function that says, I want the universe to run the source code that is me, with an input that says I'm eating tasty food. One weird quirk is that loss functions have to obey something called the monotonicity principle. This means your loss function has to be monotonic in which programs are running. This weirdly implies that physicalist agents can only be happier if more programs are running and upset if less are running. Vanessa has some ideas for why this actually isn't a problem, but doesn't have a great way to think about it just yet.
The monotonicity principle is kind of the most controversial, problematic, and weird thing about this whole framework, because the monotonicity principle basically says that the loss function, it has to be monotonic in which programs are running, in the sense that if more programs are running, this can only be, either the same or better. It can never be worse. And this is really weird if you're trying to implement something like human values, because it seems that for humans, there are sometimes programs that we don't want to run, like programs which simulate humans that are going through such terrible suffering that they would rather not exist at all. Maybe we have like a positive preference for this program not running, but that's like something that you cannot actually, well, something that's at least on the surface is not consistent with the monotonicity principle. And and to be honest, I don't really know how to resolve this contradiction. I have like a series of different ideas how this contradiction might be solved, but I don't know what's the correct thing. Like, maybe it means that we should just accept that humans are not physicalist agents, and even if the AI is going to be physicalist, you need to, take into account that the humans are not physicalist. Maybe it means that we just need to generalize the framework. Maybe the framework is just not good enough as it is. There are some weirder solutions which sound really weird, but who knows? Like, for example, there's a line of argument which says that because the universe because there is a positive cosmological constant and the universe is asymptotically de Sitter, means that within our cosmological horizon, the number of computations it's actually possible to run is finite. So if there's just a finite number of computations that you can run, then, having preferences for running something or for not running something, it kind of becomes almost the same thing, because, a computation which is like suboptimal in its running, it's like taking the slots of some other better computation that could run instead. So like in a finite universe, maybe you can kind of operationalize this kind of preferences.
So that's what we might use as a loss function. How do we use this to make decisions? Once a loss function has been defined, we compare the expected loss from different policies to decide what to do. We do this again by considering counterfactuals. We construct counterfactuals corresponding to different policies, look at worlds where I follow those policies, and see what those sorts of worlds look like according to our loss function. You can think of this a bit like our earlier example. We have a hypothesis, which is a set of distributions. We look at subsets corresponding to different policies. We look at the typical worlds in these cases. We score them based on our loss function, then take the policy that leads to the best scoring worlds.
And then what this buys you is that you end up with the belief about computation physical states and which computations are running. More precisely, it's something more complicated than which computations are running. It's like more some like which information about computation does the physical universe have. But the first approximation, you can just think about it as like which computations are running. And then when you have this thing, then this already allows you to start to connect it to the subjective point of view. Why? Because then you can also consider counterfactuals of the form, okay, I'm an agent, I'm a particular program, I'm also a program, and I can consider counterfactuals which are of the form, what if I follow this policy, or what if I follow some other policy? So these are just counterfactuals about programs, because I'm a program. And now you can apply those counterfactuals to the result of the bridge transform and see what happens to which programs are running and which programs are not running. And this thing, on the other hand, you can interpret as things that you're observing, for example, because the fact that you're making some observation, you can operationalize it as, you making an observation, it means that the program, which is you, is running on an input, which is this observation that you make. So you see that it all comes together, and kind of the subjective point of view gets, it gets a concrete mathematical meaning within this kind of objective framework.
One final idea that we're going to talk about here is how we measure the success of agents and how we can do value learning in Infra-Bayesian physicalism. If we evaluated an agent based solely on its performance on a utility function, we would be treating its policy and its source code as independent. In reality, this policy is determined by the source code. So when we evaluate our agent, we need to evaluate different source codes. We do this by introducing a metric called G, which you can think of as the intelligence or agenticness of the agent. The formula for this is given. This looks scary, so let's unpack it. First note, this quantity becomes large when the probability inside the logarithm becomes small and is 0 if that probability is 1. The probability inside the logarithm is the probability that a random policy performs better than the program. This is saying that we should expect intelligent programs to perform well on their utility function. And if it's performing well, random policies shouldn't be doing better than it very often. So this formula just captures how likely a random program is to outperform the agent's program. Lower likelihood means more intelligent. If we already know what loss function we want to use for our agent, then this is the metric we want our agent to optimize. Now that we have a notion of intelligence for our agent, we can talk about value learning. If I see some program out in the world and I don't know its utility function, how can I infer what it's trying to do? We use the following formula. The denominator is the probability we used in the formula for G. So the denominator is saying that we should expect the program to be doing well on its utility function. The numerator looks the same as the simplicity prior that AIXRP agents use, that we talked about in the AIXRP video. Basically, the numerator is saying that we should expect simpler utility functions will be more likely. And so more complicated utility functions are assigned less probability. And that's it. The equation is simply saying simpler utility functions should be considered more likely, and the program should be doing somewhat well on its utility function. If this seems complicated, the main thing you should take away is that we can make attempts to infer the utility function of programs in the IB physicalism framework, which will be this will be a part of the PREDCA protocol that we'll talk about in the next video. If you want to learn more about IB physicalism, there are a few resources out there. The original post on the Infra-Bayesianism sequence goes into lots of mathematical detail about the theory of IB physicalism. And so if you want to get more into the nuts and bolts of the math, this is a resource you should consider. To hear Vanessa talk about IB physicalism, you can listen to the AXRP podcast, where she talks about it with Daniel Filan. Vanessa has also talked about Infra-Bayesianism briefly in a YouTube video on PREDCA. Links to all of these are included below. All right, I will see you in the next video.